Hello, everybody. Good day, good evening, good morning, whatever it's in your time zone. I hope you enjoy CppNow so far. The online version, I guess Aspen would be better, but at least we still can come together and can share our knowledge here. So welcome to my talk. The topic is C++ insights and how stuff works. I'm Andreas Fertig. I'm a trainer, consultant, and author all around C++. And I happen to be the author of C++ Insights as well. So this is, once again, a special talk for me. I can share the insights and the knowledge of my tool with you. And I hope I can share some interesting things and then can show how the tool is hopefully helpful for you as well. Before we really dive into the talk, these virtual sessions are always a bit different, and we always try to get a little bit better with them. And today with me is Austin. Austin is behind the scenes, and he has the ability to turn your microphone on and give you speaking permissions. And I can ask you, if you have a question during the talk, use the Zoom nonverbal communication feature, hand raising, raise your hand. And once I see that, I will call out your name, and Austin will give you then the permission to speak. And then you can raise your question via audio if you like to do so. If you do that, be aware that this will be recorded or will be included in the recording. The other option is post your questions in the Q&A, and I will try to answer them on the go. And I also planned to have some time after the talk, 10 minutes or so, where I can answer questions. And if that's not enough, then we can head over to GatherTown and see what else is left there for me to answer. So I can just encourage you to ask questions. We are not in person, but we are still in a very good virtual setup. So use that feature of this setup. So C++ Insights, how stuff works. And I said, I'm Andreas Fertig, and I like to share, before we dive into C++, some things about another language. This is German language, because my last name has also meaning in German. It's an adjective there. And you can translate it roughly to finished, ready, complete, or completed if you translate it in English. And a lot of interesting things come up with such a last name, either in German or in English. Yeah, over the time, I collected several stories. So people often think that everything I touch is always Fertig, because this is my name, but this isn't the case. And due to this pandemic, for a very long time now, I was basically only sitting in my home, and I only go out if it's really necessary. So I couldn't collect more stories. So over the time, I shared a couple of past stories. But just this week, there was another encounter, a very funny one. I had to went to the dentist. This wasn't the not so funny part, but this was a regular appointment, so it wasn't bad either. And they offered me a new service. So they can now take amazing pictures of my teeth, I think with ultrasonic, such that they have the exact specification of my teeth, including everything like the size and shape and something like this. And they told me, well, if you want this service, you can have it. You take a couple of pictures from your teeth and in your mouth, and that's it. So I said, oh, well, that sounds pretty easy, and it's a good service for the future. So, all right, I do it. So I ended up on one of these not so comfortable chairs, and the nurse side had such a computer screen in front of her, and the ultrasonic probe. And she started scanning my first tooth. And then she was, oh no, the picture doesn't look good. The picture is not in color. I thought by myself, all right, well, it's right. I see it. It doesn't look like a color picture. And it apparently was an issue to her because the color version, she told me there she can see more. I never saw the color version, so I believe it's true, but it did already look pretty great. So she started trying in this application to turn on the color mode. After 2 minutes, she realized that she needed help. So she called another nurse and they were together looking at a screen. And then it was, oh yeah, there on the top right, there was this icon previously where you could turn on the color. And all the time, my name, Fertig, was on the top, which I thought was quite interesting because obviously it didn't get me to the state where I was Fertig. I was still waiting. So it took probably 5 to 10 minutes and a couple of nurses more to investigate this issue. And they concluded they couldn't do it. So actually, they called the company asking for help. And this is the sad part of the story. They really reached that company in time while I was there. And the answer from the company was, yeah, well, that button is broken in this release, but it will be there in the next one. We're about to fix it. And this, by the way, is the reason why you shouldn't tamper with these user interfaces when it comes to medical applications. This was not an emergency one, so it was all right. But I rather not have my UI changed on a patient monitor, which I worked a long time with. So it totally distracted all the people and it just caused a lot of time. The interesting part was after all my teeth were scanned, the nurse took from under the computer a pile of papers. And I saw them the whole time. And this was a printout of all the screenshots she had to do now to finish this whole processing of the data. And the very last sheet said, Fertig. Well, I thought, I wasn't sure whether should I make a joke about my name here being on the screen all the time or not. But anyway, this is one story, and I spot the name more often. And this Roberto he mentioned, there was also a very famous football coach, Italian coach with the name Giovanni Trapattoni, and he really scored up my name because after he lost, or his team lost the match, he was totally outraged, and due to his Italian nature and he was, I think, new to German, he ended a press conference with the word Ich habe fertig. And since then, which translates to I have fertig, something like this. So this was a joke for a very long time and it attached to my name still. So, but let's skip that and talk about C++ Insights. So what is C++ Insights? C++ Insights in general is a Clang-based tool. It's a AST transformer. Like you have other tools, you may already know ClangTidy uses Clang's AST to transform things. Clang itself is pretty good to do all these things. And the idea of C++ Insights basically is to show you what the compiler does to our source code to make it compile, or what it alters to make it compile, or whatever. So make all the invisible things visible. I like C++ very much, and I like the fact that a lot of things are hidden for us, so we don't need to write them out. We don't need to see and read them all the time, but they are there and they help us. So it's nice that we have this abstraction, but sometimes, especially when it comes to teaching C++, making these things visible again has a certain value in it. And the idea behind all this is that this transformation, the result of this transformation, should still be valid code. Because I have a couple of tests that run with the transformed version, and it's nice to see that I didn't make something bogus up, but it really is, well, it's C++ code that at least one C++ compiler agrees on. And the entire project, of course, is open source, so you can head over to GitHub and check it out, modify it. You can run it locally, or you can use the web version, which I will show you during the talk, where we will see various things. So what are these implicit things, and how valuable can they be? And what's there that, that we do not see? So there's a difference between not seeing and not knowing. We may know a lot of things, but sometimes we forget them, or sometimes we overlook them, or sometimes we are not 100% sure. So here's such an example. So 13-line program, so pretty easy, hopefully. You can also argue that it's not so much about C++ at all. What I have here is a function called max. It takes two variables A and B, and inside it is what the name applies. It figures out which of the two variables is greater than the other and returns the value of that one. And now I'm using in the function use, I declare two variables, once again A and B, and I call max with these two variables. And I print out or pass the result to a printf. It's a little bit C-ish, but I'm trying to make a point here. So, question to you are two questions, actually. The first one is, what's the output of this program? Do you know it? Do you guess it right? I see the first one saying 1. 1 is a pretty good answer. But why 1? Why not 65,530? It's max, so it's much bigger than 1. That's the first question. The second question is, I will show you the answer to the first one in a second. How many implicit conversions are there? How many implicit conversions are in this small code snippet? Think about it a moment. Here we have C++ Insights Live. This is the website. As I said, you can also use a command line version of it. And let me answer the first question I asked. We have here an unsigned short integer, and we have here a short int. And if I transform this with C++ Insights, then you can see, well, we are getting C++ code out. That's always awesome, sticking C++ code in and getting C++ code out. But now you're seeing the implicit conversions. These static casts here, these are things the compiler adds for us to make this thing compile. Because the language rules say that we cannot compare shorts. The smallest type we can compare is an int. So the compiler promotes this short for us to an integer. It's for free. That's basically the same thing as in C. And then this here is the interesting one. Here I'm passing the two variables A and B to my max function. But A is a short and B is an unsigned short. And this unsigned short gets promoted to a short, making this tremendously large value tremendously small, negative to be precise. And this is why the answer is correct. The result of this code would be that max says that 1 is greater than 65,530, because we are getting an integer overflow here, as some of you already mentioned. Now people asked, or people answered, how many implicit casts are there, or implicit conversions? And I saw during bringing up this code already, some of you said 4. And as we can see here, 4 is obviously the right answer, because the result of max, which happens to be also short, gets converted to an int as well. Because of the signature of a printf, we need to put this thing on the stack. So there we get integer. And screening the screen, I see that you all believe that there are only 4 implicit conversions. Well, let's see. Have you ever thought that 1 is not a short? It's an integer. 6500, 530, that's not an unsigned short. It's an integer. So we're getting 2 implicit conversions more here. Oh, and by the way, that thing here, well, that gets turned down to const char star. So there's obviously a little bit more going on than we usually think of or we usually need to know. The actual bug here would be assuming that 6500, 530 is larger than 1, which is, not true due to the implicit conversions. And this is one thing that C++ Insights can make visible for you. You may know it, but if you like to share it with somebody else, it's worth that you can show it to them to explain it. So this brings me back to C++ Insights as a Clang-based tool. It does a source-to-source transformation. So you bring in your C++ code, you get out C++ code, just an enriched version. It uses Clang's AST. Clang is super useful for that. So it's way more than a preprocessor because that happens after the preprocessor step. But it's an AST, so it's an early version. If you're a little bit familiar with compilers, then there's a front-end stage and a back-end stage. And the Clang AST, as I have it in C++ Insights, is part of the front-end stage. So this means basically pre-processing, parsing, creating this AST, and doing only a few optimizations like constant folding while we are on the go and seeing something like 3 + 4, that's 7. The compiler can't do that. But all the amazing things that optimizers do for us later, they happen in the backend. So passing -o something to C++ Insights doesn't change anything. So sadly, we cannot see the difference from optimizations here. That's just something you should be aware of. In the official builds of C++ Insights, they use the latest stable version of Clang. I just the other week upgraded to Clang 12, so you should have the latest features available there. And the little disclaimer is not really all statements probably are currently matched. If you find one that's not matched, then feel free to tell me. I think coverage is pretty good, but I may have missed some corner cases, especially if it comes to special GNU expression statements or something like this. So let's see another thing about C++ Insights, and I like to be honest with you, there are a few limitations, and these are templates. Templates are very hard if you get a template and try to generate code out of it, so reverse engineer it a little bit maybe. And to make this process a bit easier for me, you may see in the source this if-def insights use template. And this helps me to disable certain template instantiations. Let me show you what I'm talking about. So here, wait a moment. It's not really the one that. So I wanted this one. And if I transform this, then we can see, okay, it works, transforms perfectly. And here we have this if-def insights use template. And here you can see it either as a specialization for demo or an instantiation. It depends on how you like to see it. And this is from my primary function template func here. And it gets specialized or instantiated with my class demo, this one here below. And this code is perfectly fine. If I paste this into my compiler explorer instance here, then you will see that it compiles, but of course it compiles because the define here is not set. So once I do that, and give them a little bit of time to catch up, then we can see, oh, it says there's an undeclared identifier demo here, this one. And the reason is that the class demo is declared after the instantiation of this template. So if I move this class before the template definition, then this code compiles. So in my original code, if I simply move my class demo up here and to transform it once again, then we see, of course, that demo is before func, and this code would compile, even without this if-def. But this is the reason why I have this guarding if-def here. In general, that code should compile, but it can be that the type that it's using is defined after this declaration. And I currently use the easiest way. All specializations are directly underneath the primary template. I think it would be possible to figure out that the demo comes after that and switch things, but that's tampering with the code a little bit more than I like for now. So this is one reason for this limitation and why this if-def is there. So if you wonder, usually you can enable it, but under some circumstances, maybe not. So what is an AST? For those of you who've never seen an AST, this is an AST here. Actually, it's only part of an AST. It's only a partial AST. Anybody knows what this AST does? So very quick question, probably. And very unfair because it's a lot to read. This AST is a very simple hello world, or in this case, hello C++ program using std_cout. This is only a tiny portion of the entire AST. The entire AST on my machine contains 190 lines of output. You're seeing only a fraction of that. And this is because all the template instantiations going on in the standard library, all the tooling that goes working for us just to get out these 6 lines of code. It's amazing, but whenever you report a bug about C++ insights, try to avoid the standard library includes because they make it much harder for me to see through. But it's all right if you send one in with the standard library includes. So I'm seeing one question here. Aren't the specializations supposed to be instantiated right before the function in which they are first requested? The specialization supposed to I don't know answer to that in terms of the standard. I'm seeing them in the AST, so there can be 2 different views on that. The compiler may, and probably does, create this instantiation if it sees it, so after the class demo apparently, but in the AST, it's put under the node of the actual primary function template. So I think we can agree that maybe we are both right here, but it still gives me the trouble to figure out where I would have to place it correctly. It gets more complicated if lambdas are involved, for example. So template instantiations in C++ insights, and this I think fits into the question we had just. This is say very simple example here. What do I have? I have a class template called coolTemplate. Takes a type named T. It contains 2 data members, msize and mdata of type size T and const T star. And it comes with 2 constructors. One taking the const T star data and the size and initializes the members, and another one that's a template again, typed with a size T, and that takes a reference to an array of size n. So I'll let the compiler deduce the array size here and say that it has to be of type T. And what I can do now is I can use it in my function use here. I can say this, I create a buffer of type jar of size 5, and then I create my cool template here. And I'm just getting rid of this because I think we don't need this right now. And if I do this, then we can, of course, see as before the instantiations C++ insights shows for that thing. Here it is in the ifdef C++ insights use template. This is the pretty, well, easy stuff, and it may help you to peek behind the scenes of templates. But sometimes the things we don't see are the interesting ones, because it's a template and the compiler does only instantiate things in a template we really use or really need. And this is why we see here our first constructor taking data and size without a body. It's not used in this instantiation. Only the one taking the reference to array of size 5 is used. It comes with a body. Once I change my call here and saying I pass buffer on size 5, which I would tell you to not do because it's unsafe, then we can see that the first constructor appears with a body in my instantiation here, and the template one doesn't come with a body because it's not used. So sometimes people tell you also this, that the templates are great because you get only the code that you really need, and there's no need that the linker does optimize unused code away later. For templates, it's the case that the compiler can only instantiate what we ask it for because it doesn't know, for example, for which size should it create the body of the constructor taking a reference of an array. So this is a side effect, and you can see this in C++ insights. And it helped me once or twice to reason about which constructor gets called and figure out that this is apparently the wrong one. I wanted a different one. And sometimes this seeing something that isn't there is helpful as well. So the other thing I encountered while I developed C++ insights is a pretty basic thing. It's about default parameters for functions, and I think we all know that they are there. We all probably know how to use them. We may probably avoid them because, well, there's some issue with them because they're hiding something, and it gets more complicated if you have virtual functions with default parameters and overload them. But this is how we define a function with a default parameter. I have this function func here. It takes an int x, and I default initialize that one with 23. So this is my default parameter. And of course, I can then call in line number 5 func without any parameter. I never questioned how this works because it just works, and hey, sometimes it's good if something simply works and I do not have to care about why and how. But while I developed C++ insights, I stumbled over how it works by an accident, because C++ insights at some point did it out of the box because I fired up the magic. What the compiler does is, in all the places where we call func without this parameter, it simply injects the value at the call side. So there is no other magic going on. It's just syntactic sugar, putting this 23 in all the places that are needed, which is much better if we would do it, because then there is a chance that sometimes it's 23 and sometimes it's 32 or some arbitrary different value over time. So this consistency we get by the compiler here, it's pretty easily achieved. I'm not a compiler developer, so maybe easily achieved for us is not true for implementing this feature, but as it turns out, it's just a little bit shuffling around. I hope it's easy for them too. And that's one of these funny things. I think it's interesting to know. And it's good to know that they are so easy and there's no tampering with the function itself. So it's no special magic going on. It's a bit similar to this one, default member initializers, which we got in C++11. I have this function here, or this class, sorry, it's a class init, and it comes with a default constructor where my member I is initialized to 9, and in lines number 7 to 9, it has 3 different variables declared inside the class I, v, and s, being of type int, std vector of int, and std string. And I use default member initialization here to initialize I with 0, v with 2, 3, and 4, and s with hello. And usually in classes, several questions come up. The first one is, how does this work? So is there something special going on? Because the promise is that all these variables get initialized with these values. And that seems, it's a new syntax, so it seems a bit new. And the other question is, what's with my variable I? Does this get initialized 2 times? So first to 0 and then to 9, because I re-initialize it in the constructor. And for this case, it doesn't really matter because it's an integer. But if it would be the std string, then maybe it would matter because we're copying data or allocating data here. So if we transform this in C++ in sites, then we can see let's make it shorter. Then we can see what's happening. What's happening is really simple. It's like the syntactic sugar we saw before. All the default values we provided here, they end up in the initializer list of the constructor, as we can write them. It's just nice the compiler does this job for us and preserves the values. So it's 3, 3, and 4. It's hello. And of course, my variable I gets initialized only once. It's C++. What did we expect? The 0 here is the default that only takes place if I would not provide another value. And once I provide a second constructor, let's say 1, take in an integer. I do not care about the parameter itself. It's just for the demonstration to have a second constructor. Then we can see, oh, now my integer is initialized to 0, as we probably expected. And all the other variables are initialized to the defaults as we specified them here. And this makes our code more consistent. And as you can see, that the transformation shows that what's going on underneath is it's the same as we can write it. It's just, once again, nice that the compiler does this for us. It saves us a lot of trouble. And C++ Insights helps you to make it visible again, or to see what's going on there. And sometimes there are more hidden things that C++ Insights can help you to see. And this is one of them. I don't know who of you all remember C++11. In C++11, it was the first time we had Constexpr, so we could make functions Constexpr. As I show it here, I have this struct cpp11, and it comes with a single method fun, and this one is marked as Constexpr. It returns a bool, and it always returns true, just for the sake of having a method here. And if I transform this in C++ Insights, guess what? There is not really much happening in the output here. It's the same as we put in, except for that little thing here. Our member function gets marked as const. And we didn't specify that initially. And our compiler also gives us a warning saying that a non-static member function will not be implicitly const in C++14. And you can see this. Once we switch to C++14, the const goes away. And why do we care for this? Because if in C++ we are now in 14, I declare this method once const and once non-const, that works. But in C++11, of course, it doesn't. Because I now have two functions that are marked as const. Because that one gets implicitly marked as const. And the danger here is that in C++11, we use or can use this function in a const context, so for a const object. But we can not do any more in C++40 because there the const is dropped. So the advice here usually is to put const to your methods in C++11 already when there are Constexpr. And this is one of the transitions between standards which C++ Insights can visualize for you and can help you to see what's going on there. And it saved me once or twice the explanation why this is the case. So, but now let's move on to something different. Let's talk about lambdas and captures. I have this class test here. It comes with a single member variable a of type int in line number 2. And it has a constructor in line number 5, which takes another integer and we store this integer in x, or in a simply. But then in the constructor's body, I declare lambda on line number 7, L1, and what it does is it captures by copy and it returns a plus 2. So the member variable of test plus 2. And then I use a printf to get the result of L1 printed out when I invoke this lambda. I increment a by 1, so the a from the class test, and then I print out L1 once again. And you can see it below. Test initially is initialized with 2. So I would say 2 plus 2, that's 4. So the expectation is that I get 2 times 4 in the output, correct? Who knows what the output is of this code example? Any ideas? I hope we agree on the math. Yeah, 4 and 4. Yeah, that's at least the expectation. The truth is 4 and 5. Correct. It's 4 and 5. And you can either believe me or you can head over to CppNow and hack it in and see whether I'm lying to you or not. But believe me, well, try to, that the truth is it's 5. And I'm not showing you CppNow for this, but here's what C++ Insights can show you. Why? So first of all, I assume you already heard that a lambda or a closure type internally in C++ is modeled as a class. And it comes with this special thing. It's a call operator. We can write this ourselves. And in that call operator, we find our lambda's body. So this is what we wrote here. And here's the capture. And now you can see that inside this closure type, we have a variable of type test. It's a pointer. and it's called this, or underline this. This is a capture the compiler does for us because I requested that we capture by copy. Okay, but A is part of a class, and I requested capturing by copy. That means the compiler captures, as we can see it below here. Where is it here? The compiler captures this pointer of this class. And this pointer is a pointer. So we capture a pointer. We capture the copy of, or we store a copy of this pointer in the class. And hence, when I increment A outside of the Lambda, I see this effect when I invoke it once again, because this, and this, they are the same. They're pointing to the same object. So this is usually not what you want. Sometimes it is, but it rarely really is, because we expect it to be different. And the simple fix here is use Stardust or dereference this as the capture here in line number 7. So this essentially tells the compiler to not simply copy the pointer, but dereference the pointer and copy that. And if you look at this in C++ inside, here, if I simply say here that I like to capture Stardust, and I transform this, then we can now see that this time the captured variable here is test. It's an object test. So here I copy the entire object test. And hence I'm no longer seeing the difference here when I increment A, because this is just a copy of what it was when we captured it. So this is what you usually want to stay safe here, usually. So, but when I do this, now I captured the entire object. And on the previous slide, I only had one variable. Now I have two, A and B. So I increased the size of this thing by one integer or by 100%. It depends on how you try to sell this thing too. So saying that you doubled something, that often seems good. It may not be the most difficult thing here, or the biggest burden to have an integer more, but think of it in a bigger scale, then it may matter. So I only like this single variable A to be inside this lambda and not the entire class. And what you can do here is using a C++, another C++ feature called init captures, where you can say something funny like A equals A here, which means that you like to capture A by copy and create a new variable A inside the lambda. That's the capture. And now we can see that I end up with only int in my closure type in my lambda. It's only the int A. And if I change this, then I can do this. Now I can see that the captured variable inside a lambda is, in fact, of a different name than the one outside. And I'm never sure when I use this feature whether A equals A is the right thing to do or to give it a different name, because both ways have their drawbacks here. A equals A seems confusing, but epsilon equals A, yeah, it's a different variable then, so it lacks of another level. C++20 brought us templated lambdas. And before we talk about them, let's see what we can do before C++20. This here is an example using C++14's generic lambdas. They were already a very great improvement for lambdas. So I once again use this function max here, which in this case is the result of a closure type, or it captures a closure type. And it does the same thing as we saw before. It takes two parameters, x and epsilon, and it tries to figure out which of the two values is the greater one, and then returns that one. And I assign this entire closure type, this entire lambda, to my variable max here. And just to be having said that, please use the std_max function and do not come up with your own version. I'm using this for illustration purposes only. So having this max function here, I'm now able to say in line number 7 and 8, max 2,3 or max 2,3.0. And that works. And this is only half great, because I don't want line number 8 to compile. I'm mixing types here. I'm getting, once again, integer promotions or promotions to floating points, because 2 and 3.5 are not the same type. One is an integer, the other one is a float, but it compiles. And if you look here once again behind the scenes, with C++ insights, if I transform this piece of code, then we can see, yeah, of course, we already learned this. My closure type is a class. And here you see the call operators before. The difference being this time it's a template. So it's a template call operator. And the compiler creates two class or type names for us. It names these parameters. And it then creates the function signature or the call operator signature using that type name and the desired variable names. And below here, we can see it gets instantiated once for int and the other time for int and double. And here we are once again seeing the casts I don't want because, well, this is just a different type. And preventing that line number 8 compiles in C++ 14 or 17 isn't that easy. There are ways to achieve that, but usually they are, well, ugly and like a workaround. They may include decal type and other stuff, and this is not really what I want us to do. So C++ 20 changed the game. In C++ 20, we can have templated lambdas or lambdas with a template head. You see that one in line number 3. Lambdas with a template head allow us to have the angle brackets after the capture clause and before the lambdas parameter list. And in these angle brackets, we can use the same things that we can use in other template heads from templates. So I can say here type name T, I can also say size T or whatever I like that's possible in a template head. So I can use non-type and type template parameters essentially. And what I can do now, the power I have is that I can say type name T and I can use this T for X and epsilon. And you can look at this like a regular function template. My line number 9 now no longer compiles because templates care about types. And first of all, if I compile this or transform this, and we can see the difference to C++ 14 is nearly nothing. So this type, it's type name because I said so here. If I say class, then it's class, so the same that the compiler does, but for some reason I often use type name. And the difference is that this time the compiler doesn't have to come up with a name. We, or I in this case, already told it a name, it's T. And I can use this for all the variables or the parameters. And if I try to compile the second line I object to, then we can see that we get this usual answer from the compiler that my candidate template is being ignored because there was a conflict introducing the type of the parameter T int versus double. So this is exactly the error I want. I like as often to do something here and not silently discard this error because my lambda takes another type and doesn't care that X is of a different type than epsilon. And this is something that C++ 20 gave us with lambdas with a template head. And there's a bit more in C++20. So consider this example. I have the struct keeper here. It comes with a std vector of int member. It's called data, initialized with 2, 3, and 4. And then there is some kind of an access function called items to get access to this std vector, but it's returned by reference. I try to fit the code on a slide, so imagine this code a little bit bigger and data being private, and then there's more going on, but this is essentially what we need here. We access data through items. And then I have this factory function or something. Here it's called get in line number 7, and what it does, it returns me a default keeper object in line number 9. Really simple. And now in line number 14, I have a range-based for loop, because range-based for loops are so great, and they really are. So we are using them all over the place. And so do we here. And what this range-based for loop does is it should iterate over all the values in data by calling get.items and iterating over them, creating a new variable saying items, and this is a reference to the actual item in there. And then I'm printing these items out. And now, depending on whether you consider this luck or bad luck, this might actually work, but it doesn't have to, because it's undefined behavior. If you look at this in C++ Insights, we can spot the following. Once I do transform this, then we can see, now let me choose, it's a bit shorter. So I just flipped between lib.std++ and libc++. They generate different names in the output here because they have different standard library types, and the libc++ ones are a bit shorter, so I prefer them for demonstrations, but for the speed of your library, it doesn't matter at all. So here we see what's going on. We're calling get.items here, and we are in the range-based for loop. A range-based for loop by the compiler is modeled that a new scope is opened, and then in scope, the compiler creates 3 variables for us: range, begin, and end. And then we look at the regular for loop, where we find a comparison between begin and end for not equal. So the compiler tries to figure out if we already reached the end or not. Compiler takes care of incrementing our iterator. And then here in the body of the for loop, the compiler dereferences the iterator for us and assigns the result to item, just as we asked. And then we see the rest of our body, the actual printout. And now here we can see it a bit more clearly what's happening. Get.items. Get returns me a temporary object. And then I call .items on it. But this temporary object is bound to a std vector reference, not to a const reference. So we don't get lifetime extension here. This means essentially that the contents of this object are invalid after we hit the semicolon here, after we finished this full expression. Making this code undefined behavior. So there's a likelihood that it works because the things are still there on the heap or on the stack, and you may illegally access them, but there is no guarantee that it works. And we usually like our things to work guaranteed and not just sometimes and sometimes not. And this is a very sad part because usually range-based for loops are the right thing to go. And this is not just because of this problem, but we can address this problem with C++20's range-based for statements with initializers. I will show you the difference in C++ insights, but I'd like to mention that Nikolai Yosutis tries to fix this issue in the standard by getting a lifetime extension for the code that I showed to you, but it's probably going into C++ 23, but it's too early to tell. But there is a huge interest to fix this because it just creates problems. And this is a workaround. So what we can do here, or what we have here, is the same code as before. The difference is that in C++ 20, we can have initializers for our range-based for statements, the same way we can have them for regular for loops. And now if I transform them, or this code, then I can see that in this case here, I'm binding it to an R value reference. So I can also make it plain auto if that's better. Doesn't matter. Now I get a copy. But now in both cases, this thing stays alive for the entire for loop, and this is what you want. So you want this lifetime extension regardless which way you choose here or chose. This is what you want. And this is what you can get with C++ 20. Of course, you can work around this in C++ 17 and before by declaring the items variable here before the range-based for loop, but that kind of defeats the purpose of having everything neatly fit together and not spread all over the code base. Oh, there's an interesting question. Can C++ insights be used to see the copy features used? Give me some time to answer this. There's a slide for that later on. So before I finish with the range-based for statements, here is one other use case I like to show you for the range-based for statements with initializers. This is the probably more one that was targeted by this feature. We now can declare variables for our range-based for loop to be used there and to be in the same scope. And we can use this, for example, to declare an index here, which we then use to print out when we iterate over our vector to see which element we are currently looking at and the value. And it behaves the same as before. There's a variable declared inside this compiler made-up scope just before the actual magic of the range-based for loop. You can see this here quickly in C++ inside. So this is the code here. Didn't want to more. So now instead of my keeper object, I'm having here my size t. I still have this range begin and end. And I can use this idx variable here inside this range-based for loop scope safely, and it will be destroyed after line number 10. So this is the idea behind it, and that's probably the better use. The other one is just a workaround for a buggy for loop or range-based for loop. What else do we have in C++ insights? Or not in C++ insights primarily, but in C++. In C++ 20, we have spaceships. Isn't it awesome? The three-way comparison operator, or spaceship operator, or consistent comparisons. There are a lot of names. And the basic promise here is we have to write only one comparison function, namely my operator spaceship, and the compiler generates all the others for us, namely less than, greater than, less than, equal, greater than equal, not equal, and so forth. And this is brilliant. I mean, getting this for free, having more consistent comparisons, did all sells. Question for me always is, how does this work? That's really interesting. It's a case where I have to write only one function and the compiler creates 6 others for me, or 5 others for 5 additional ones. So I have to write this code here. I create a spaceship. It comes with a member X of type integer, and it has such a spaceship operator. It returns a std-weak ordering, which is also a new type we have for this operator here in C++20. And it takes a const spaceship reference value. And the cool thing is I can default this like other special member functions. So this is the signature for my spaceship operator. And then I use it. In line number 10, I create a spaceship, and in line number 11, it's Enterprise and Millennium Falcon. And I couldn't decide which one is the really better one, so I assign 2 to both of them. And then in line number 13, I'm comparing whether Enterprise is less than or equal to Millennium Falcon. And this compiles, this works. So how does this work? Here is C++ Insights. And here's the code from the slides. And if I now do the transformation, then we can see a little bit what's going on. The compiler here below calls an operator less than or equal for us, which is in the global namespace, and it passes the result of enterprise.operator spaceship passed Millennium Falcon to it with an internal type of this library implementation to 0. So this is one of the times where I would favor showing you something different, because this is internals of the standard library. This is nothing really interesting, but here it's about the value 0. And this shows that my operator spaceship returns a value, can say -1, 0, and 1. And my operator less than now compares it to this value. Standard libraries are a little bit free here what to do, but this is the implementation. So this is one operator returning different values and another operator comparing them and figuring out which one it was. This is the magic at this point. But there's a bit more to see. Here I have my equal operator. I haven't written them down here, have I? I haven't. But the compiler generates it for me as part of the spaceship operator. Under some circumstances, I lose it, but here I have it. So this is another interesting fact. But there's something that's even in this code with C++ Insights hard to see or impossible to see because it's not happening. Let's say we change this example slightly and that we do this. We bring in our own operator equals and say that we want it to be able to compare to a single integer. And then we compare whether RHS, our right-hand side value, equals X. And now in line number 13, I'm calling it, I'm asking whether enterprise equals 2. Now let's have a look at this code in C++ Insights. If I transform this, then at the top here, we can see, of course, this is what we asked for. This is the operator. And below here, there is nothing funny going on. It's exactly what I asked for. It's enterprise equals 2. And we can see here, I haven't mentioned that so far. Of course, we see that it calls operator equals for the enterprise object. So pretty boring, right? But behind all this spaceship stuff, there's another very interesting feature. What if I like to say 2 equals enterprise? Do all of you feel already this this pain which we had to go through in C++ 17, 14, and so this won't work because we have a spaceship object here. We can compare this one to an integer, but we cannot compare an integer to spaceship object. We cannot write this comparison. So what we had to do in C++ 17 was to come up with a friend operator or something similar. Now it's C++ 20 and the standard evolves and it gets better. And this is, I think, whenever I show this, people say, whoa, so it's probably a more hidden feature of Spaceship, but it's equally awesome. First of all, this thing compiles. Okay, here. It exited with result code 0. And you don't see a difference here. But it compiles. It's this code. It compiles. And the reason for that is that the compilers in C++ 20 mode have a new ability called operator rewrite. They can flip the operators. So what they actually do during their overload resolution is they create the case we had before, so enterprise.operator equals, and they can flip it around and can later say, okay, if that combination doesn't work, does the other one work? And then they can flip the operands for us if they see in the overload set that it will work. And this is what happens here. And this is why this code compiles. And this is why you can save so much code in C++ 20 by getting rid of all these friend declarations and making simple code simply compile. In this case, there is not so much that you can see in C++ insides because it's still enterprise.operator equals. But you can at least see that if you flip it on the left side, it doesn't change on the right, which is interesting and surprising. But the reason is operator rewrites, compilers have this power, this ability, and they are allowed to do this. There are also a couple of other things we can see, but they're not so easy to spot. So if you look at the spaceship operator here, it currently says that it's const, and it's inline, and it's Constexpr. This is what a compiler does for us or adds for us. Now, if I start doing this, I see it doesn't work because I created this operator equals here, which makes the compiler bail out, providing the default operator. But now it did. Now I can see that this operator equals is const and no except, while my spaceship operator is still only const. Once I start using the spaceship operator, we can see that the spaceship operator now is const and no except, while my operator equals is solely const. Would I use both? Then we can see there are both are no except. And this is not so much interesting for you because once you start using it, it gets no except, but it's the compiler saving us probably a few CPU cycles during compilation because it doesn't evaluate whether this operator can really be no except or not as long as it's not used. So here we can see a couple of work that can be delayed by the compiler. Of course, this is Clang, GC may do it differently, but they delay it until it's really used, then they evaluate whether it's no except or not, or should be no except or not. And they do not do this check upfront, even if it's not used. So this is something that appears as a side effect that you can see this in C++ insides. Now, so far we talked a little bit about the bigger things, I would say. So let's talk about the little things because they also matter. This is matching the little things part. This is a little C++ program or a small C++ program. I have a struct test, which doesn't have any data members, and I use this in main by declaring a variable a. So let's see what C++ Insights tells us for this code snippet. If I do the transformation here, then we can see nothing. There's nothing to show because there's nothing going on. So simple struct without any data members. There's nothing the compiler should or has to do for us. What if I add an integer, say x, and do the transformation again? Well, what I'm seeing now is that here in the praised initializer, I'm now getting this init. It's 0. It's what the default or the praised initialization does at this point. But still, other than that, there is not much going on. I can also use the in-class member initialization. Then I'm just seeing the echo here. I'm seeing that it's defaulted. But still not much going on. But it's a struct, right? Maybe if we make it a class, what's then going on? Oh, now we have a constructor. But we have this constructor not necessarily because it's a class, because by making it a class, my member became private. If I use a struct and make this member private, then I get this constructor. And we had a question before whether C++ Insights can show us the use of copy constructors. So say I have a second instance, let's call this B and initialize it with A. Then we can see the copy constructor popping up here. And if I would do the assignment, then we can see the assignment operator coming to this trio here. Okay. There's another thing you may be missing. It's a struct now. It has a constructor, but it has no destructor, right? It has no destructor because it doesn't need a destructor. My integer doesn't need a destructor. So let's add something that needs a destructor. Let's say a std string. And once I do this, we see a destructor because my std string requires one. So does my class test by that. So here you can see how things are popping in depending on the types in your type. And you can also see that the compilers are very, very generous with us and only provide the things if they are needed. They don't just pitch them in because they should be there. They only do it if necessary. So let me quickly read through the questions. Why does compiler insert equals and test equals A? So you're asking for clarification. This question is about this here. This is my poor way of trying to show what a constructor would do. This is wrong C++, and it works because it's ending up as a copy constructor here. But this is my way of showing that there is a constructor call going on. There is sadly no better way to do this. I hope this answers the question. So this is not exactly what a compiler does. This should only show that there is a constructor call going on. And the other question is, Could the example with test A generate output which includes the designated member initializers? I'm not sure if I understand the question, so if I remove this for now, so I could say here x equals 4, but I'm not sure if this is the question. And of course it can't, because now it's no longer struct, or the members are not public. I'm not sure if this was your question. I had the output with test 0 here, that one, you say. And there's no real reason to transform this one, if I understood this right, into the designated initializers. It would probably help you, if that's the question, to make it visible. But technically, this is what the compiler does here at this point. And I just see that Jason raised his hand. So Jason, you may speak up. Oh, this was an accident. All right. So then, what other questions have we? Why are all the constructors in comments? The constructors are in comments because I haven't tracked this down really. In earlier versions of the standard, I believe there was a difference between us defaulting the constructors versus the constructors are there by the compiler. This changed the class. And I think it changed in some standard, but since then I haven't updated, and I tried to keep the struct or the class as it is and not tamper with it by adding these things that the compiler added. So this is the case where, this is one of the few cases where I put the things in comments to not change the actual behavior of the class. All right, there's another thing I like to show you. And I think it still counts, hopefully, as the small things, despite that Nikolai Yasutis wrote an entire book about it. So I don't want to go too deep into it. But let's have a look at this modified little thing version here. I still have my struct test with my public member I. Now I have a function func, it returns auto, and it has a variable of this type test declared inside t, and it returns that t. And if I transform this in C++ insides, we can see one interesting thing. At this point already, the compiler knows that it will apply a technique that we know as NRVO, named return value optimization. And this is something that C++ insides shows you at this point. This variable t here will get the NRVO benefit, so it will be constructed at the return point actually, and not really on the stack at this point. And the book Nico wrote is about move semantics. And when people often start hearing about move, they feel the urgency to move all the things. And it seems wise to move this t at this point because, well, we don't want to pay for a copy. But remember, the compiler already told us here that this is an NRVO variable. Once I apply std move to this return value, it's no longer NRVO because we tampered with it. So the compiler refuses to do NRVO, and it's all right to do that. That's in the standard. So this is the reason why most of us all the time tell in training classes, don't apply std move to return values, except to really know what you're doing and except it's really necessary at this point. But C++ insides can help you to see this little difference at this point and peek under the hood and see, oh, okay, this may be the wrong point to apply std move, or this may be the right point, however you like to see it. So this raises the question, what can C++ Insights do for you? And let me be honest with you, I don't know. This is entirely up to you. I can only share my experience with you. And this is that seeing things is a very valuable thing. Even if you know that's there, it really helps if I can put C++ Insights on and show it to you. Talking about code since I created C++ Insights without actually having something to show and just talking about it, that drives me crazy. So I often tend to use C++ Insights then, so in my training classes all the time. It also shows that something I learned from Matt Gottbold's Constexpr to have this interactivity. So I have my code snippet here, I transform it, I see the transformation, people start asking questions, I change them, and we can see the transformation. It's the same as we do on Constexpr. We put our C++ code in, we see the assembly output, we change it, we are surprised that it changes or doesn't change in the assembly output, whatever. It creates much more questions. It makes people wonder about more things and asking them and then thinking about things. So classes tend to be more interactive if I use C++ Insights. It can also help to settle opinions about differences. Despite that it only visualizes Clang, it often is enough if there is no argument between whether GCC does it differently. If it's just about the language, then it does a great job. And it's a little bit like all the IDEs we have. C++ Insights can visualize the template instantiations. It has the benefit that it can do it for a larger piece of code. If the IDEs I saw, if I do it, it's more on a spotlight. And here you have the whole transformation. Sometimes this is a bit more what you like, but other than that, it's very much the same as you may have it already with your IDE. And there's one other question. Is there a way to see hidden friends or the injected names into our namespaces? I honestly don't know from the top of my head. We have to check this out. Probably it does. So what can you do to support a project? Of course, it's source code. You're all developers, so you can come up and patch something that's buggy or add a new feature or whatsoever. Head over to GitHub and send me a PR or open an issue report because you found an issue. That's also highly appreciated. I try to fix them in a timely manner, but creating issues or telling me about issues, it's also really good. You can head over to Patreon and donate a little bit of money to fund the project and then cover the server and domain costs. And if you like to get something in return, then you can head over to the Spreadshirt shop and get you some of these nice t-shirts with the C++ Insights logo on it. I hope you had fun so far. And I like to close with, for now, I will be around for questions after this talk. And as I said, we can communicate in Discord or see each other in GatherTown. I hope you learned something about C++ and maybe C++ Insights. And at this point, I'm fertig.